Our last speaker of tonight is Frederik Schulz. He is a software engineer working at Centrifuge. He will talk about storage migrations from solo chains to parachains, a topic that has gained a lot of attention right now because we see more and more parachains launching each week, as Centrifuge experienced quite lately. Welcome, Frederik. I'll let you take it from here.
All right, thanks for having me. As already said, I'm going to talk about storage migrations in this workshop, and I'm going to focus on the part of when you have a standalone chain and you want to migrate data to Parachain. So why was this interesting for us in the first place? We at Centrifuge, what we do is we're a company that enables real-world asset financing via blockchain technology. And for this reason, we have a standalone substrate-based blockchain since beginning mid-2020, and we currently use it to anchor our NFTs and reward our asset originators. And now that we also got a Parachain slot at Altair, and also running for one on Polkadot, what we want to do is we also want to bring our product that we currently have on Ethereum, is we want to bring this product to the Parachain so that we have better integration with the Polkadot ecosystem. And this was the reason for us that we already have a running chain that we need to, that state we need to be migrated to our Parachain. So this is why this was really relevant for us. And a quick overview of what I'm going to cover in this workshop. I'm going to start to talk a little bit about the storage, how I see it from a runtime perspective, and especially what I think is important to consider when you're doing a runtime migration. And then I'm going to show you multiple ways that you can use to actually migrate data to a substrate-based parachain. And I also show you the limitations of each approach. And I hope I can give you some guidance on when I think it is reasonable to use which approach. What I won't cover, I won't talk about what you actually need to do to adjust the node or adjust the runtime so that it is compatible with the relay chain. And quick outline here. I'm starting with basics, basically with the background about the storage. Then I'm going into the 3 ways that I see that there are for storage migrations, talk a little bit about the pros and cons, show you some examples and some code examples also, and also walk you through the migration that we did just recently in Altair. And then I'm going to summarize it in the end, just rather briefly, and show you the resources so that you can go through the slides and the code yourself after the actual presentation. So let's dive directly into the storage. From a runtime perspective, the storage behaves like a key value DB where all the keys are built from the names. So, from this perspective, it doesn't really matter that the keys that you're building here are actually the Patricia paths for the actual DB, but for your runtime, it's just like I give you a key and I get a value back. And what you can see on the right side here are basically the 3 types that Substrate provides, which is the storage value, the storage map, and the storage double map. And as you can see, how you construct the key from those names is then you hash the palette name, and this is system specific with the XX hash, and then you hash the item name with the XX hash, concatenate the 2, and this will be your final key for storage value. If you give it to the database, it will give you the value there. And for the map, there's just one additional part, which is basically after the palette hash and the item hash, you're concatenating the hash of the key with a hasher that the actual developer can choose. So, but again, you just have a key, you give it to the database, and then you get a value back. And for the double map, it's the same, just that you have 2 variable hashes that you can use. So what's the takeaway here for migrations is basically know your hashing algorithms that are being used and know the naming. And what I'm showing you here on the right side is basically just the two interfaces that the storage provides the runtime with, that you can use to actually access the storage. And we have two interfaces here. We have the typed interface and we have the unhashed interface. And by the way, this is not valid Rust code, but just to get to the point is, in the first example on the top right, you see that I want to get the total assurance. And what I'm doing is I'm using the storage value interface and use the get call. And what the get call does for me, the underlying logic is basically it's hashing my palette name, it's hashing my item name, and then it's accessing the database and giving me the value back as a typed value. And the same goes for the storage map, where I'm using basically the frame system account storage, and I'm saying, okay, get me the value that is associated with this ID, and the underlying logic is building the key for me, and then I'm getting the value. But what you also can use is you can also use the unhashed interface, and in the example below, you see that we are also getting the total assurance, but instead of letting the code build the key for us, we are building the key ourselves. So we're saying, okay, hash me the balancer string, hash me the total assurance string, concatenate the two, and then get me the value. And what we are actually using here is the typed get call interface, which is saying, okay, I want this to be decoded into a balance. And there's also the raw interface, which is saying, again, we are mimicking the call from the frame system account get call above here. We are building the key with system and account, and then we're using the Blake2 128 concat hash with the ID, but we are not getting an actual type now because we're using the get raw interface. We are getting just bytes, and it's now our responsibility to actually decode it. So why do I think this is important for migrations? When you consider a standalone chain that you have and you have a parachain, what you could possibly do is you can change the palette names and you can change the item names on your parachain. This is possible, but when you consider the example of I want to migrate my system account information, and I fetch the state and I get a set of keys and associated values, what I need to do is I need to cut out the part of the key for a value that belongs to the palette name and the storage item name, and then rebuild this key with the new names, concatenate it again, and then inject it into storage. And when I do this, it will actually be at the right position in storage where runtime expect it to be, and then it can retrieve the actual account informations. Where you need to be a little bit more cautious is when you're handling actual maps or double maps, where you have keys that are probably user-defined that you're not aware of. And here it is, when you have a transparent key, it's not a problem because the transparent key basically signals you or shows you the actual key at the end of the hash. So you can even change the variable hasher on your parachain here, because again, for account information, you retrieve the keys and the values, and you just cut out all hash part and just get the ID. And now you have the actual key, and then you rebuild the whole part before that. This is basically hashes. And then you inject it into storage. And when a user now says, I want my account information, what the system is doing, it's creating the hashes that it's expecting the storage to be at. And because you use the same logic, the values will be at the same location. For non-transparent keys, this is, of course, a little bit more different, because at this point in time, you don't know the actual ID, so you can't use the ID and hash it again. And for this reason, you can't use the change the variable hasher in this case. All right, so much about storage. And now to the 3 possible ways that I currently see that there are to migrate data to Parachain. There might be others, but those are the 3 that I considered here. And the first one is fairly straightforward. When you use you can use your Genesis spec, and the Genesis spec is basically you define your state, and then at block 0, your storage gets populated, and then you have the state in your chain. And this is super simple to use. I think everybody does that because everybody needs a chain spec. It's safe and it's verifiable, which is really nice because you can basically hash your chains back, hash your chains back, and then everybody can verify that it's the same. A big con is that it's static, and especially the state knowledge that you need to have at a certain point is rather difficult for standalone chains, because when you're a standalone chain, as we have one, what you're doing is once you want to be a parachain, you need to register for Parity. And when you want to have a crowd loan to do this, you even need to do it in order to open a crowd loan. And when you're registering for such an ID, what you need to do is you need to say, this is the hash of my Genesis spec, and this is my WASM blob, so that I want to use. And at this point in time, you basically fix the state that you're at. And you can imagine that when, I don't know, you're fixing your state with the Genesis spec, and 6 weeks later or 2 months later, you're actually getting a parachain slot. At this point in time, or in between those points in time, your standalone chain will basically stall, because all the blocks that are being, if it's even producing anymore, but all the blocks that are being produced are basically invalid, because this state won't make it to your parachain. So for us, this wasn't a use case, so I won't talk any more about this, and we'll go directly to the second approach, which is using runtime upgrades for this logic. And runtime upgrades are basically, there is just some logic that the substrate-based chains, frame-based chains trigger when you do a runtime upgrade, and then you can just put any logic on your pallets on runtime upgrade logic. And what you see here on the right side is the actual migration of some data, or transformation, better said, of some data in the frame systems account palette. And what we're doing here is basically we're saying, okay, translate me all the data that I have in storage to a new data type, and then inject it back into storage. And what you typically would do when you use this kind of logic to actually migrate data is you would get your data from your chain, probably store it alongside your palette in, at best would be, I don't know, fixed array, scale encoded values. And then in this logic, in the migrate all, or in any logic that you put in your runtime upgrade logic, you would just access this data that you have in your WASM, and then you can transform it, inject it into storage, maybe even access other storage elements if you need to. But this is the way to actually migrate data for via runtime upgrades. And the pros of this are definitely the data is still verifiable because everything is in your WASM, so everything is on chain, and you have the free the free logic that the program gives you. The big con on the other side is that you still have a size limit for blocks. So when you look at the right side here, and the percentages might differ because this is from our chain, but it's still the same for every chain. You have a part which is blue here, which is for normal extrinsics, reserved for, or the maximum amount that normal extrinsics can take. And you want your on runtime upgrade logic to be at most this big. So you want at most on runtime upgrade logic and on initialized logic to be 75% of the block, because the 25% above that, the yellow one, the operational ones and the mandatory ones, those are the ones you still want to be in a block, because those are the ones that make the block valid, basically. And this is a little bit harder because, to the best of my knowledge, there are currently no benchmarks for the on runtime upgrade logic. So you're a little bit in a try and error phase where you need to think about how big can my on runtime upgrade logic be at most. And you only have a single block also. So when you have a rather large state and you think, okay, this won't fit into a single block, what you need to do then is you need to chunk your data set into multiple runtime upgrades and run them one after the other, but be cautious with the point that users should not be able to actually interact with your chain in between, because you're in some weird state at this point. And of course, the WASM size is still relevant, because if you have more data that you're migrating and the WASM is getting bigger, this is still relevant for you. So I would say use this one when you have a dynamic and rather small state after Parachain registration, but don't use it when you have a large state. And when we arrived at this point, I was thinking about this at this point where I did this, and I was like, okay, maybe it's possible to have it runtime upgrade logic about multiple blocks. So maybe this is possible. So, and the requirements for those were basically create some kind of logic that runs over multiple blocks, of course, but you don't want any extrinsics to be included, and you still want it to be triggered by the on-runtime upgrade logic. And when you look at the right side here, this is basically how a block is processed. You first have there above that there's even the on-runtime upgrade logic, but you have on initialize, you apply the extrinsics, and then you finalize your block. So what I thought, okay, if we can manipulate the building of the blocks in a way that that we create blocks that are valid, but don't allow any extrinsics to be included over a larger range than the actual on-runtime upgrade logic, we can just call any logic in the on-initialize through over a period of time. So when you look here at the code and you look at the self-client new block add call, and the propose with function here is basically proposing a block. What you're doing here is basically you're saying this code is basically running the on-runtime upgrade logic of every pallet and the on-initialize logic pallet, and all those functions return a weight. And this weight is already included in your block builder. So your block builder is kind of pre-weighted. And below this part, you see where we iterate actually through the inheritance that your system has. And below that, what you can't see is the part where you actually integrate extrinsics. So when your block builder at this point in time where you have called the self-client new block add, when it over a period of times has a weight that takes all the place for normal extrinsics while still leaving enough place for inheritance, you basically block the chain while still being able to run some arbitrary logic that you want to run. So what I did then, so this is the dummy palette that I created for this presentation, and doesn't represent the one that we tried out at first, but it's the same logic. Is we have a dedicated palette which has some on runtime upgrade logic, and when a runtime upgrade is triggered, what we're saying is, okay, please take the current block and put it into storage. And the onInitialize function always just checks, are we in the range where the current block is between starting block and between the number of blocks that we want to run the migration for. Of course, when you have a more dedicated approach, you probably would have some way of accessing the data that you want to migrate at this point. And I don't know, having some kind of structure or some kind of trait that tells you this migration is going to be so big. And then you can calculate basically how many blocks you need to block the blockchain for. So, but for the dummy logic, this basically works out to show you that this works. And what we're doing then in this logic here is we're just for the sake of the demonstration is we are depositing an event which is saying, okay, the migration is in progress and it will run for n blocks now from this point onwards. And then I also have a endow account function which is showing some examples on how you can alter the storage then when you're in this logic. And when you look at the last row here, this is basically the important point where we're saying this is the weight we are consuming here. So we're always blocking the chain to the point where no normal extrinsics can go in anymore and returning 0 otherwise if you're not running in a migration. So the endow account logic is fairly simple. It's just we're creating just enough entropy to create a single unique account per block. And then we decode those bytes into account ID, also create the amount that we want to endow, decode this one into a balance, and then we create the account info, which is the one that we want to inject into storage. And as we are just creating balances out of thin air, we should also take care of adjusting our total assurance. So I'm using the type interface here, as you see. I'm getting the assurance and then I'm overriding it with a new value. For the account info, this is not so simple because the account info actually depends on the account data type, and our compiler currently doesn't know which data type we are wiring in here. So, but it's still able to generate me a final key. So what I'm doing here is I'm saying, okay, for this account that I want to inject, generate me the final key, which is correct. So I don't need to do this myself. And then I'm using the unhashed war interface, which is basically just saying, give me this bytes, this key bytes, give me this data bytes, and I will just inject it into storage. And you must take care of that being the right ones. And then I'm depositing the event. All right, and now we can start the demo. All right, yeah. What you see here now is I already onboarded in my local setup the Parachain to my relay chain. So I'm producing blocks and I'm now triggering the runtime upgrade. And this will take some time as the data is a little bit heavier, of course, here. But at the point in time where this is in the block, you can see in the events that we have that we will actually producing the events that we just saw in the code base. So the validation function has been applied, and when we reload now, this will actually show you that we are in an ongoing migration. So the events is here, basically we get the next block, and at this point, we will have the endowed account and we will have a saying event that's saying, okay, for 8 more blocks, we're blocked now here. And in order to show you that it's not just the event, but actually the storage work still works, or the storage is still of the type that the runtime expects, I'm just adding this account and then, getting the account information, which is, I have 1,000 there here. Yes, but nobody can send them because we don't have a private key, and no proxies in place. But and this will go on and on for 8 blocks now. And as I said, it's super important that we don't allow normal transfers or anything to happen in between. So what I'm doing now, I'm just saying, okay, Alice, send my endowed account this amount. And this will actually fail now because this is the best of my guesses. I think the signed extension will still contain the older runtime version, and this is the reason why the signature is false. So I'm getting the new metadata, and when I trigger the same transfer now, it will go through. And as you can see now on the top right, it's actually ready. So, but although it's ready, so it's proposed to the pool, it's not being included into the events. And what you will see now when the extrinsics, the last one will go through, you will actually see that the balance transfer happens directly afterwards. So it's in the waiting line, and if it doesn't die before that point, so it's not too old, then it will be directly included because it's the next, it's the up running one. So of course, when your search migration runs for fairly long, you might also come to the point where all extrinsics that are being proposed die, but yeah, at this point it works. So migration is over, we include something, and then I'm just showing you that, all right, it's over now, and that the value of the account actually changed. So accessing the values that we injected into storage works quite well. All right, yeah, this was it basically. And now I'm coming to the third point, and also coming to the point of why we choose to not use this one. So to not use the multi-block runtime upgrade. So because although multi-block runtime upgrades are good, when you use extrinsics here, you still need to create a special palette. You still need to expose extrinsics to inject this data, and you should ensure sudo access. Or you want everybody to inject the data that they want to, but this is up to you. And the pros of this extrinsics approach is definitely, it's simple, it's benchable, which is really nice, because you can basically say the normal substrate mechanisms that provide you with the security to build the right blocks is still in place if you bench it right, you know. And for this reason, it's multi-block by design when you block your chain for the time you're doing such a migration. The big con on the other side, and I think, and this is a part that is really not negligible, is that it's not verifiable, at least the data that you inject. It is, of course, because you can check the state and everybody can check if their values actually match and something like this. But in contrast to the WASM that is actually part of your runtime, you're just injecting data from a pseudo account. And I would say use this approach when you have a dynamic large state after your Parity registration, but don't use it when the others are possible. And our reasoning for this approach and not using the multi-block runtime upgrade was we already had a fairly large state at the point where we thought about this, where I approached this, and it was, I don't know, roughly 1.2 megabytes for account data alone. And what you always need to consider, and this is scale value encoded stuff, so what you always need to consider is that all this data that I'm injecting into my WASM, it must be part of my WASM. So for the 1.5 megabytes, I don't know how this is currently our size, I think, that you already have, you're just adding data that you want to insert. So at this point in time, as runtime upgrades and parachains were I think at the beginning where we thought about this, it was rather unclear how big can your WASM be and what's the maximum size. Is it possible for us to actually weight our on runtime upgrade logic in a way that our relay chain will accept all the blocks, or will we stall at one point? And we thought, okay, pseudo is available anyways at the beginning, so this approach is the safest one for us, and also the one which is the most straightforward at this point. And what we then needed to consider also was, because our standalone chain is a substrate v2 version, basically, so we needed to consider some transformations for the data that we wanted to migrate. And we also needed to consider the possible time deltas that we have, which is especially important for vestings. And of course, state consistency is important, because otherwise, yeah, you have a corrupted state, which is fairly bad at this point. So what I'm going to do now is I'm going to walk you basically through the 4 data sets that we wanted to migrate and show you the palettes and the extrinsics that we developed here. And first of all, what you see here, our palette is tightly coupled with everything that we need, because we don't want to refactor this. We just want it to be easy to be used. So, and this is super convenient for us because we have typed access to storage, and we also have access to the trait implementations. And the data sets that we wanted to migrate is basically the total assurance, the accounts, the proxies, and the vesting. So those are the 4 data sets that we wanted to migrate, and those are the 4 ones that we expose extrinsics for. Now, the total assurance migration is really straightforward and easy. As you can see at the top, we have a migrated balance insurance here. We have a weighted balance insurance extrinsic here, and what you get is you actually just provided with an additional assurance. And what we're doing here is we are calling the storage and saying, give me the current insurance. Then I saturating at the additional assurance that I have. So I have a new one, and I could have used the type interface here, but I used the raw one. And with the raw one, I'm basically saying, give me the key, inject it into storage, and that's it. And then I'm depositing the event and saying, okay, we're done here. So this is really straightforward. The accounts migration wasn't more complicated, but we needed to think about this a little bit more, because, besides the migration that we did for the actual data, the transformation between the data types, between the v2 and the v3 version of account info, we also needed to think about the fact that, okay, there are a lot of data in this one that doesn't belong to our new chain. So we reset the nonce, we reset all the ref counts at this point. And also for the account data, which basically in the balances palette holds your free, reserved, miscellaneous frozen, and fee frozen amounts. We're basically saying we remove all frozen ones, and we also remove all reserved ones and put them to the free amount because all those reserve values and fee frozen, all the stuff belongs to our standalone chain, and governance staking is everything that is fresh in our new chain and is probably not even used. For example, staking is not even used currently, so we can't introduce this to the new system. So we thought about transform it now as a clean one and introduce locks and ref counts later on. And then the actual migration is fairly simple. Again, you have a weighted extrinsic, and what you have here, you have the accounts, which is basically a vector of a number of accounts where the first element of the tuple is the key scale encoded, and the second one is the account info scale encoded. And then we just check, is it too much, because we have a limit so that it's not overweight, and then we just iterate over the vector and inject it rawly into storage. And afterwards, we're just saying, okay, we have migrated n accounts, and saying, giving the post info back of saying how much weight this extrinsic actually used. Now, the third data set that we migrated is the proxies migration. And there's also a transformation that we needed to do from tuple to proxy definition. But this was not complicated. This was same proxy types, just everything in an actual struct. But what is a little bit complicated is the fact that there is some difference between anonymous proxies and normal proxies. And the difference here is basically that for a normal proxy, what you have is you say as a delegator, you say, I want this account to be a delegator of me, which means this one can act upon myself. So, and I'm the one who's saying this. So the system reserves some amount on my name, which is totally fine. And for anonymous proxies, we're basically creating a free account without a private key, just account at the moment, and saying this one is I want to be a delegatee of this account, but this account doesn't have any value. So we are reserving some amount on the creator actually. And in order to detect this, we think about, okay, if we find an account that is part of the proxy storage, and the reserved amount here is less than the number of proxies times the per proxy amount plus the base amount, then you can be 100% sure that this is an anonymous proxy. And the other way around, it's not fairly trivial. But this was our approach to actually detect anonymous proxies. And why this is relevant, I'm showing you now in the extrinsic, is here in the extrinsic, which has a pretty ugly types in the signature. But what I did here was basically saying, if you look at the for loop down below, where we actually iterate through the vector, is saying, okay, I have the key, which is the account ID, I have the reserved amount, and then I have the tuple, which is my proxy information, and the deposit. And the thing here is the deposit solely means overall in the system, we have this reserved amount, but it doesn't necessarily mean that this reserved amount is on the delegator, because for an anonymous proxy, this is not true. So the reserved amount that we are providing here is basically saying, this is the actual amount that you need to reserve. And then when you look further down where we have the reservable currency call, we're basically reserve the reserve amount. And then if this is okay, we inject the actual data into the storage via the typed interface. All right, now to the last one, the last data set. This is the vestings migration. And what is important here is that we need to take into consideration that we have a block where we take the snapshot. And we have a block where we take where we execute the actual migration, and those might be apart quite significantly from one each other. And what we need to do is we need to call vest manually at this point, because otherwise the time that has passed in between will basically a time that the account hasn't vested. So what you need to consider as a parachain when you're coming from standalone chain with a 6 second block time is that as a parachain you have 12 seconds now, and the important vesting states are basically ongoing, ended, and not started. And when you look at the if-else logic here, the second else if is basically I'm finished. So this is trivial. We're just saying, okay, you're getting everything at the first block. If you haven't started yet, we're saying we're introducing locks now actually. So we're saying this is what we want to lock. This is the new per block. It's twice the time because the blocks are twice the size from seconds time apart. And the new starting block is basically just a new starting block, taking into account what has already passed. What's a little bit more complicated is the part where you have an ongoing vesting. And what we are saying here is basically we calculate how many blocks remain, how much remains locked. And then we're basically saying we're just creating a new schedule, because we basically just say as if you just got a new vested transfer with this amount and the rest is free, which is basically calling vest for them. And when you look at the extrinsic now, what we discussed a little bit was the add testing schedule trade function here that we can use is actually rather complicated with respect to how many locks it introduces. It also does some dust cleanup, and there's a lot of logic going on. And what we wanted to do is, and this is why we use this interface, instead of introducing the locks manually, we're just saying we're using the interface that is substrate provided and that is that somebody looked at and that is verified that it's working. And use it in order to inject the new schedules. And this will also for us do the resolving of finished vestings and all the stuff. And again, at the end, what we're doing is we're simply saying we're finished now. We have migrated this vesting information for this account, and then we are giving back the post info with how much weight we actually used. All right. This is roughly the end now. I will quickly summarize what I've just talked about in a hopefully understandable manner. I think there are 3 ways to actually migrate data to Parachain, and it is possible to use multi-block runtime upgrades, but I think there will be probably a way better approach in the future for this. And I hope I've put enough emphasis on the fact that there are many pitfalls that one can fall over when you're doing a migration. Yes. Thank you for your attention. That was basically it. And you find the resources on the right side. And if we have time now, I'm open for questions if there are any.
Well, thank you so much, Frederik. It was really, really good talk. I think that community will be really happy to just follow up your options. And I think regenesis and then on-chain migration and the last one, just extrinsic. It's really, really, probably really good ways to go. I think I have a few questions. It's mainly I would say, for example, when you tried the runtime update, runtime upgrades, did you have to pause both chains at the same time? So you were saying that you block just to reject all the new extrinsics, but are you blocking on both sides or on the Parachain, and you also block on the standalone chain?
No. This was I think this was maybe not well explained. What I did here, I just paused my Parachain while I'm connected to a relay chain, and the state I got before that point from a standalone chain. So I'm fetching the state from a standalone chain, putting it into a WASM, and at this point with this WASM, I will trigger a runtime upgrade, which will take care of blocking my Parachain so that normal users cannot do anything in this time. And when I'm over, I'm just over. So yeah. So the
Okay, yeah,
standalone chain
makes sense. Yeah.
basically what you need to consider always is at the point where you take a snapshot of your chain and you're saying this is the state, everything that comes afterwards on your standalone chain is basically irrelevant. So
Yeah, yeah, I agree. I was thinking on that scenario where you have like the auctions and you need to wait all this period and then see if you are gonna get the slot. So probably it's gonna be really difficult, right? Like to really use that method if you need to stop the chain and then just like wait and you will see if you get the slot or not, right?
yeah. I've talked about it quite a few times. I think with you at Parity, and I think this is also in the making of thinking about how you can seamlessly onboard and offboard a chain. And to be honest, Substrate is really huge, and it always amazes me that I come to a point where I'm at a completely new code base and I'm just lost in a rabbit hole, and then I need to pause because I need to work. But yeah, and I think there's a lot of stuff that I don't understand why this doesn't work, but I think in the future this is something that you considered, I think, as far as I understood.
Yeah, yeah, that's right. We are taking a look to probably other type of migrations. I also wanted to ask, like you said that you benchmarked the extrinsics, but like, did you force like you push down the value of the weights just to make cheaper when you are like adding the new storage on your chain on the parachain, or like you really use the direct benchmarks?
No, I directly benchmarked them. Yeah, we just wrote the normal benchmark setup that we have. I came to the point where I noticed that it's just the easiest to always call the scale decode one if I want to ease the compiler. So this is for me the easiest way because I'm in testing environment and I know that I have legit data. But yeah, it was just a normal benchmarking. And of course, we benchmarked it on different machines, my one, cloud one, so that we have a rather reasonable idea of how heavy it is. And it worked, luckily. So yeah.
Okay, yeah. Thank you so much. I think there are no more questions. So thank you again, Frederik. It was really good talk.